So let's talk about the process. And if you're going to make your own, the bits that you need to understand. The first thing, which we're going to talk about, actually, in simple cases, you will not have to concern yourself with, but it's important as things get more advanced to understand the basics of the concept. And that is, here in these examples, I've been jumping around all kinds of different things. So I've dealt with things like images, I've dealt with things like text, I've dealt with things like, um, well, colors, and more images. So very different kinds of data. And the way that the machine learning frameworks that we've built all work is that you first of all have to convert those into a vector of numbers. And that vector of numbers is going to be the features that we are going to look for patterns in. Now, if the thing is already um, in numerical form, then of course you're already there. The numbers are, or a vector of numbers is the features already. But very often we have to do some level of feature extraction in order to turn something into um, into a vector that we can then process. And we deal with this at a high level with this feature extract command. There's a choice of algorithms behind and lots of details that you can control. But the basic idea of this is to take some samples of data. So here I've got a string in color and a date. And we've got several examples of that, and it's going to examine those and convert those into a simple feature vector of 3 numbers to represent each. Now, this is normally when you're doing machine learning, you're dealing with quite large amounts of data, so proper patterns can be found. I've given it hardly any information here, and so it's done some rather naive things. It's decided that this is a phrase um, uh, of some kind, and it's mapped that to a number. That's clearly one number is never going to represent the entire richness of uh, of a the human language. And in fact, this number doesn't necessarily correspond to this. This number is the first feature of a set of 3 vectors that represents the whole thing. So it's taken that whole set and mapped that to some kind of space that is in 3 dimensions, and then converted that to a number. Now, these things start to become meaningful when you have larger amounts of data, but we accelerate the process when you have small data by leaning on some pre-trained feature extractors that make these things make sense. And the idea is that the feature extract can work over any kind of data. So if I give it this sort of key value data set, then here it's converted these things into a set of pairs of numbers, or I've taken these much more complex things of graphs, and it's turned those each into a vector of, in this case, it's decided 6 numbers sums up the number. Now, it's kind of useful to imagine that these things represent something that is descriptive. So you could imagine, for example, in this graph, maybe this first number is something like how dense it is. This would have a higher number than this one, or it's how pointed it is, or how connected it is, or how central the most central point is, or something that we might have words for. One of the things you have to accept fairly early with machine learning is that it's inventing its own concept. So while we might look at a picture and say that's a cat because it's got pointy ears is our version of extracting a feature. In its world, it's going to invent some concept which might best be described as zigzaggy splodginess or kind of prickly jagginess or something, but it's a concept that it's invented that may not even have a word that we would even recognize when we see the patterns, and it's building this language for itself that it then ascribes numbers to. So these things are important, but not very easy to understand. So one of those ways we can understand them a little bit better sometimes is to try and visualize them, because sometimes that can give you a sense of what the extraction means. And I also want to show you what this looks like when it goes to a bit more scale. So let's do something now that's a kind of got a semi-real set of data to it. And I should run this straight away because it will take a minute to run. I'll apologize in advance here. I'm doing live web image searching. So if the internet throws back anything inappropriate for me, I apologize in advance. But what I'm searching for here is 3 characters from the Guardians of the Galaxy franchise: Rocket Raccoon, Groot, 4 characters, Gamora, and Star-Lord. And I'm doing a web image search to get thumbnail pictures, just to keep the speed of this, the amount of data small for this demo example, I'm going to get 20 images of each. So in a few seconds, hopefully, we will have generated 80 fairly random images that match the image search. We might find that there are some things that are not correctly found from Google, that maybe instead of Rocket Raccoon from Guardians of the Galaxy, if there's a picture of raccoons in rockets, then they might come up. But if you have enough data, those kinds of things tend to average out. So I think we're done. Let's fetch those. So let's have a quick look at what we've got here. So here's our data set. There's Rocket Raccoon, some Groots, and so on. So let's hide those again. We don't need to see those. In this case, I am going to oh, actually, this was meant to generate a random sample that I was going to show, but so here is my random sample of just, no, it's actually, so randomly sampled the whole lot, so it's reordered them in order to be not in an obvious pattern order. And we're going to do feature extraction on those. Now, in this case, it's going to start doing not just how do I map that to some numbers, it's going to also start doing a certain amount of feature reduction. So we're going to accelerate this feature extraction with things we've learned from looking at millions of other images. So it knows to look for things that are kind of, say, pointy or square or round, or things that turn out to be significant features in the real world, or certain textures. And then it's also going to reduce that. And the idea of dimension reduction is that we're trying to get fewer numbers that represent the essence of what we've got. So if in fact every one of my images has in it the same texture at the same value, there is no point keeping that number because it's not descriptive of the differences between images. And in another context, if you imagine maybe I was trying to predict what kind of breed of dog it was by its height, weight, and length and color, you might find that that height and length, because dogs are basically in the same aspect ratio, once you know one of them, you know the other. So it's not worth retaining both numbers. It might be enough simply to keep the length of the dog because the height is kind of inferenceable from the length. In practice, reduction takes the whole space and squashes it down to lower space, combining different features together. So it's nice to think of it as throwing out the numbers that aren't very useful, but actually it's doing something a little bit more complex. But the basic idea is that we can sum up these images, which are all, I don't know, 100 pixels by 100 pixels. So there's 10,000 values in each. I guess 30,000 values because they're in color. And we have squashed this down now to a vector, which is, let's just find out how long that vector was, a vector of 78 numbers. And those 78 numbers are starting to learn what's important to sum up this picture compared to the other pictures that we saw in the data. So one thing we could do, for example, with that is they do the same process, but build a nearest function that retains every image together with its extracted feature value. And now when I take a new picture, I can find the feature vector, the 78 numbers, and I can find the vector in that list that is closest to those 78 numbers. And that point in that space corresponds to the picture that has this most similar set of numbers within that feature space. If we're extracting useful features and reducing the dimensions appropriately, what we find is we get something that looks similar. It's not similar in the same, it's facing the same direction, but it's got the same kind of features in it than our sample set. And again, I'm saying here what's the nearest to this picture. So these are the two that are closest in that vector space of features. And now you can start seeing how these rather abstract numbers start to become useful because we now have a measure of how close something is to something else. We can find the nearest thing. We can start finding clusters of things that are near to each other. And all of these things come out of this idea of a reduced feature vector for the content. Now, one very useful thing that I do as a kind of first step is we take this to the extreme and we take those pictures and we squash them down to a feature space of 2 numbers and treat those as XY coordinates and throw the pictures onto a plot using those XY numbers. And when you, as a first step with any machine learning thing, it usually gives me some sense of plausibility of whether um, there is something useful to be found in those features, or whether the features are just irrelevant. If all we took out was a feature that was the top right corner pixel, that might turn out to be completely irrelevant. And what we can see at a glance here is we start getting clusters forming quite naturally, where we can see down here, here's a whole collection of raccoons together. We've got a whole collection of Groots together over here. Um, uh, I'm not seeing Star-Lords in the group, but I'm guessing they're in there somewhere. It seems like we've got a lot of things in cartoon form together. So when you start seeing clusters forming in a feature space plot, or things that you can recognize as being similar or appearing close to each other, that's a good sign that this approach is going to work. This thing itself is not terribly useful, except as a qualitative measure of, are our features doing something useful? But it's a good first step. And all that's actually doing is taking our vector space and squashing it down to 2 dimensions and plotting the points, labeling them.